Hello, I'm Mr. Klein, and I'm here to welcome you to your first calculus lesson. Every time we have one of these lessons, I'm going to be doing some writing. Anything that I write down, I encourage you to write down as well. You'll notice that it says Lesson 1-1. That is referring to Unit 1, Section 1 in the Forrester textbook, which you have access to. I want to just start by making sure that you know what calculus is. Have you ever heard of a paradox? A paradox is two things that seem like they could not coexist, but perhaps they do. And the paradox at the heart of calculus is the paradox of time. Let me explain. Everything that you do takes time, takes an interval of time. You got up, you took a shower, that took some time. You had yourself a nice big bowl of Super Frosty-Os, took some time. You brushed your teeth, you took some time. Drove to school, that also took some time. Everything that we do takes an interval of time. However, you can never experience an interval of time. It's impossible. The only thing that we ever have is now, the moment we're in, an instant. And that's the paradox of that is at the heart of calculus. That everything takes time to do, but all we as humans can ever experience is a single instant. With that in mind, let's begin today's lesson. Today's lesson is called Rates of Change, or as I'm going to call them, ROC, also known as ROC or ROC, because calculus, it rocks. Anyway, it's the first day of class, and rather than doing a big lesson, I was thinking maybe we could go to the beach. In fact, I already mapped out the route for us. Okay, here we are, Warren Dunes State Park, beautiful long sandy beach, large sand dunes. It's exactly 200 miles away. Now, this time right here is what would happen if you were speeding. I know we're all law-abiding citizens, so we're not going to do that. Let's suppose this instead. Let's say that we go 200 miles. That's the distance to the beach, right? And it's going to take us 4 hours. And my question for you is, what is going to be our average rate of change? On this time interval. Now, if you just thought to yourself, Mr. Klein, it's going to be 50. You're right. And what you did, if you said that our average rate of change is going to be 50, is you said, well, I'm just going to take the change in our position or our displacement, or in other words, how far we drove. And I am going to divide that, because I know that rates are when you divide two things. I am going to divide that by the change in the time. And 200 divided by 4 is going to give us 50 miles per hour. So fantastic. You know how to find an average rate of change. Now, if our average rate of change was 50 miles per hour, how fast were we going right here when we were heading through Kalamazoo? Were we going 50 miles per hour? Were we going faster than that? Were we going slower than that? The answer is that at that instant, we can't tell. The fact that you're going 50 miles per hour on average tells us nothing about how fast we were going along the way. I mean, for instance, we could have zipped it out of the metro area and then just driven really slowly the last bit of the route. Or we could have slowly sped up as we were driving. So there's not enough information to tell exactly how fast we were going right here, unless I tell you something else. Suppose we know that the distance that we've traveled, d of t, is equal to 100 multiplied by the square root of the time that has passed. So this is how many miles we've traveled. This right here is how many hours have transpired. Okay, and I want to look at a picture of this graph. Here we go. So you've got a first quadrant set up. In the miles direction, I would encourage you to go 100, 200, 300. I know we're not actually going to drive 300 miles, 400, but make it go that way. Then in the hours direction, let's pick some hours that are easier to plug into the square root. So for instance, if I plug 0 in here, our output is going to be 0. And if I plug in 1 hour has gone by, our output would be 100 miles. And if I plugged, 2 is not so good. Let's plug in 4. If I plug 4 in here, square root of 4 is 2. 2 times 100 is 200. So at 2, 3, 4, it'd be at 200. And then just for giggles, let's go one more. If I plugged 9 in, right, 9 would be an easy number. 5, 6, 7, 8, 9. The output would be 300 miles. So our distance traveled over time looks something like that. Okay. And let's go back to the average rate of change for a second. If I asked you for the average rate of change from time 0 to time 4, you could represent that this way. You could say, well, rates are slopes. And if I'm looking at a graph, the average rate of change is just going to be the slope of the line connecting those 2 points. So here's our average rate of change on the interval from time 0 to time 4, which would be equal to this line right here. It has a name, a line that connects 2 points on a graph. Anybody? Anybody? That's right. It is called a secant. So it'll be the slope of the secant that connects the endpoints. Okay. And so in this case, let's see, I know a slope is just that slope formula, right? The y1 minus y2 over x1 minus x2. So that would be, here the y value is 200 minus here the y value is 0. Here the x value is 4, and here the x value is 0. Numerator is in miles, denominator is in hours. So this would give us 50 miles per hour, just like we got before. Now, with that in mind, here's my next question for you. How fast are we going at time 4 when we arrive right here? Are we going the same speed? Are we going 50? Are we going faster? Or are we going slower? Well, the answer to that question is that our instantaneous rate of change at this moment right here at time 4, how fast we're going right then, is also a slope. But this time it's not the slope of a secant. It's the slope of this tangent line. This line that approaches the curve and then moves away from it and touches it just at that instant. So you can see that the slope of this line is considerably less than this one right here, which tells us that our instantaneous rate of change is going to be smaller than 50. Okay, and let's make a note here that the instantaneous rate of change at time 4 hours is equal to the slope of the tangent. Now, how do we find the slope of that tangent? Not so easy, because this time we've only got 1 point, right? So the remainder of the lesson is going to be figuring out how to get that slope right there. And spoiler alert, right now we can't find the exact value. We can only estimate it. Here's the idea. We want a slope. In order to get a slope, you need 2 points. What do you need? You need 2 points. Can't do it with 1. And in order to get 2 points, I've got one right here. I need to pick another one. And the other one I'm going to pick is just some other time that is close to 4. So let's say this. we're going to sketch a little table right here. Let's pick an interval. Now, again, what we want is the slope of this line right here. That's going to tell us how fast we're going after 4 hours. And so I know that I want the interval to start at 4 hours. And I also know that I want to pick a time that's pretty close to 4 hours for my end of the interval. So I'm going to go from 4 hours to 5 hours. And then over here, we're going to approximate. It's not going to be exact, but we're going to approximate the instantaneous rate of change at time 4. An instantaneous rate of change I'm going to refer to as the IROC. Okay, so we need to plug in our two endpoints. Anytime you're finding a rate, it's just a slope. So I know this is going to be 4, and this is going to be 5. I already figured out that at time 4, I had traveled 200 miles. If I want 5, I'm going to need to use the calculator. Okay, so I'm going to get out my calculator. If you don't have your calculator out, pause the video and get it out. Let's see. The distance that we had traveled after 5 hours would be 100 times the square root of 5. I am getting that just from plugging 5 into this equation that we defined as the relationship between hours and miles. And that gives me 223.606. Don't be bashful with the decimal places. Go far on these. So as I'm simplifying this, what I see is that from time 4 hours to time 5 hours, the distance that I traveled is this minus this, which would be 23.606 miles. And the time that took me is 1 hour, which means that our estimate of the instantaneous rate of change would be 23.6 miles per hour. Okay, so there's an estimate. Now, is that the best estimate that we can come up with? Okay, definitely not. What could we do that would give us a better estimate of how fast we were going right at 4? Well, one suggestion is this, that going from 4 to 5 is too large an interval. Let's make the interval smaller. So we could go, say, from 4 to 4.1. 0.1 of an hour is only 6 minutes. So this is going to be like the average rate of change over those 6 minutes. And look what happens. Here's 4. Here's 200. This would be plug in the x value of 4.1. This right here would be, let's see, 100 square root 4.1. I got 2.024845. So now let's see. Only 0.1 of an hour transpired. In that time, we traveled a distance of 2.4845 miles. Oh, dividing those is just moving the decimal place over by 1. So a better estimate of how fast we're going is 24.8 miles per hour. Okay, now obviously we can get an even better estimate by making the interval smaller. That interval has a name. It is called the tolerance. The tolerance is technically the size of the interval. And the tolerance that we're going to use as a standard is 0.001. So what we want to do is go from 4 to 4.001. Okay, now I'm going to be quiet for a minute, and I want you to go ahead and find this one on your own in the calculator. Pause the video right now. When you're done, come back and check your work. Okay, we're back. Here's what it should look like. You plug in 4.001 here, you plug in 4 here. We get these two numbers for the distance traveled. So what's happened is that over a very small interval of time, we've traveled a very small distance. When we divide them, we get 24.998 miles per hour. One thing that I really want to caution you about is this. If you don't go enough decimal places right here, what happens is you get a distorted answer when you get right here, okay? So make sure that you always go lots of decimal places. In conclusion, I want to close out with this. I got an idea. What if we could get a really good estimate if we knocked the tolerance down to 0? Right? Because if we knock the tolerance down to 0, you can't go any smaller than that. And check this out. 4, 200, 200. I come up with he traveled 0 miles over 0 amount of time. Uh-oh. I don't know what to do with that. What is 0 divided by 0? Hey, if you want a good time, take out your iPhone and ask Siri, what is 0 divided by 0? She's going to give you a kooky answer. But what I want you to know is that this setup right here, where you have a 0 divided by a 0, is going to be an important part of our story this year. Not today, but shortly. And this has a name. It is called an indeterminate form. Just what that means is that when you run into these situations where you have 0 over 0, we don't know what's going to happen, and we have to run little experiments like we did right here to get an estimate of how fast we're going. Okay, congratulations, you made it to the end of your first lesson.